next paper is called Attribute-Aware Nonlinear Co-Embeddings of Graph Features. And Ahmed, Rashed from Brazil.
We know that traditional recommender systems always deal with simple user-item interaction graph, which is a bipartite graph. And sometimes this entities graph have some information or contact information, which introduced a new family of models which are actually aware models and contact-based models. Those family of models are performing very well when you have attributes, but sometimes if you try to apply them back in a situation where you have missing attributes or some attributes that you are dependent on are non-existent, they tend to underperform. And selecting a simple model that's from scratch optimized for non-attributed entities will perform, such as matrix factorization. So our aim in this paper is to define a model or find a model that can work on attributed entities and non-attributed entities, at the same time have consistent performance, so it does not degrade if you in a different situation. So our aim is not to find a complicated one to beat everyone else. We are trying to find a simple one that fits well. So the problem formulation, we have a set of users, and those users might have some attributes or information, and we have a set of items that also might have some attributes of contact information. It depends on the profiles that matters. And we tackle the problem of gradient prediction, mainly because most of the literature we are comparing with also were optimized for gradient prediction, so we have to use the same ground for evaluation. So the proposed model is divided into 4 phases. So the first phase is attribute-aware nonlinear embeddings. So we define a tower embedding function for every entity we have in the graph. So for example, in this case, we have a tower embedding or embedding function for users by u, and we have an embedding function for items by I. This embedding function is a series of fully connected layers that have some nonlinearity. And simply the input vector for this function will be the user ID and any attributes that you might have. In the same case also for items, that you have the item ID with any feature. So it seems simple, however there are some tricks in it. So we use the concatenated grammar for nonlinearity, so it's not relevant for operational nonlinear activation functions, and also we use activity regularization across layers and not that step or dropout. However, dropout also shows a very consistent performance for validation, so you can still also use dropout, which is kind of performance. With the scoring function, we can go with very simple scoring functions as dot product, so dot product you can use numbers, or you can use a parametric one. But most of the experiments show us that dot product can perform pretty well. So until this point, what we introduced we can see as a deep generalized nonlinear matrix factorization that's attribute-aware. So starting from the next phase, this part is influenced or inspired by the graph embedding domain. So in graph embedding domain, people start to use the Laplacian matrix of the graphs in node classification process. So this Laplacian information is extracted from the node adjacency matrix and their degrees. So we try to leverage this information also in recommender systems. But in recommender system we have a slight problem here. So this is a bipartite graph. So it's not a normal graph where you can just apply any graph embedding technique. So the only way to do it is to either apply this indigenous graph embedding technique or try to approximate this Laplacian information or imitate it somehow. So what we did, since we are aiming for a simple flexible model, we tried to imitate this feature. So what we did, we extracted the weighted adjacent matrix from the interaction graph, we shifted and normalized this adjacent matrix as a green one, so it maintains the same sparsity as the original adjacent matrix. You can send it in sparse format. And we just concatenate here the extra column and extra row with the degree, normalized degree of nodes, which are the usable items. And at the end, you can use the columns as the item features or rows as the user features. And since it's sparse, you can do sparse multiplication in the first layer, so it will not hurt the performance. So how we use these features, you can simply concatenate them with the rest of the features. Finally, how we optimize optimize this loss, we optimize it to quadratic losses and mistakes. And we have this regularization of the output percentage, weights. So we did this experiment on 3 datasets. And those 3 datasets were movie lens datasets. Datasets are attribute-aware datasets here. And the last datasets are much sparser. And it only contain content-based datasets, no attributes. So what we did, we followed this experimental protocol. We had evaluation across different percentages of ratings. So we have this model scale across different things. And this is for the movie lens. And if for the red picture, there is a use 3 ways that we have training set, validation set, and test. And of course, we use RecSys for evaluation just to match the literature. So this is the first experiment for movie lens under K. So you can see here the graph model without graph features, so it's just a nonlinear matrix factorization. You can see it's performed well against other models that similarly use inside information. So this part here doesn't use inside information, and this part here is a model that contains inside information. So GraphRec without inside information and without graph features is performing well with other models similarly. But once we added the graph features to GraphRec, we saw a significant improvement that we did not expect. We were expecting an improvement that's slightly above attribute-aware models, but still better than non-attribute-aware models. But the significant improvement was even better than attribute-aware models, but just using graph features. So, and what also we find out that you can still add the side information for even more heuristic. So those 2 features have different characteristics. You can combine them if you have them. The same findings we found here on the movie lens large datasets, movie lens 1 million. So you can see here, when we don't use any side information, it performs well. But once we add the side features, it performs almost better than all other customized attribute-aware and content-based models. So the same finding, and also the same finding where you can add side features to get it even slightly left. But you can see the left decreases once you add the features, the graph features. So the amount of gain will decrease if you add the graph features. So if we go now to sparse dataset with context-based, we use the sparse dataset for a specific reason. And I will explain why in the following slides. So you can see here actually the graph features is very good in performance. So without the graph features it's better, and it's also better in the context-based. Also some interesting stuff here. You can see the factorization machine is better than some models that was introduced in that piece. And for some reason, factorization machines are left out as a good basic applications. Don't know why, but this is one of the takeaway from this. So why we have here bad performance? It's mainly because the sparse is pretty easy. So it's very sparse, which means the graph features are really empty. So you don't have any features. And we will do a specific study in this case with data. So here you can see our study on different activation functions. And we saw that this concatenated variable can be activated in both negative and positive direction. It's better than random, which is better than linear, and sigma is not performed very well. Every column here is tuned separately with its maximum achievable performance. We did another study where we see if these graph features can have positive impact on other models, not just ours. So we add these features to both SVD and factorization machine, and we found that those models can also leverage some gain from these graph features. And you can see the gain for more complex models or more linear models is higher than just simple linear models. So, and this is a study where we try to find why graph features, so graph features are not very helpful when you have sparse information. And here, it's a study of those features, so side features and graph features, or users and items that have different rating scales. So here you have the whole scale of rating frequencies, and you can see here if the user has very low rated frequency, the graph features are not really helpful as much as the side information. But as you can increase the rated frequency of the user, you have more interaction, the graph features tend to be as equal as the side features. And of course, combining both is the best option. Also, graph features are very helpful in cases where you have noisy accounts that are bots or group accounts that has too many ratings. And in this case, side information most probably will be fake or will be one of those accounts or one of the users that have this account. So in this case, also graph features will help while side information will provide incorrect information. We don't have the problem here in items, but you can see increasing also the ratings for every item will increase in performance. And you can also see while if you have too few ratings for items, the graph-based feature will not help a lot. Once you increase this rating frequency, you can see the graph-based feature become even better than the side features, and combining both of them will also increase the best performance. So we proposed GraphRec. It's a simple text model you can apply to a situation where you might have attribute entities or unattributed entities. And fortunately, it achieves part accuracy on those 3 data sets. So we see our main aim. Our main aim was a simple model that people can use later. And we also found out that graph-based features have higher impact on dense data sets and for user items and interactions. And finally, the future of the extended GraphRec context-based and session-based information. Thank you.
Thank you very much, Ahmed. We have time for a few questions. Any questions?
Thank you for your talk. So you reported improvements on RMC loss, right? Did you try to compare results on rating metrics, something like MAP or NDCG? Because improvement in RMC does not always translate in improvement in these metrics.
Yes. So in this paper, we did not report on other metrics. We mainly report on RMC because most of those baselines, we already use those numbers from their papers. And some of them we tuned from scratch, specifically this factorization machine and linear factorization machine, so NFM. Those are tuned from the scratch, but the rest we took directly the number from the baseline papers. That's why we also use specific experimental protocols that exactly match the papers.
Okay, thank you.
There is a question from the overflow room. Is this the first one?
Hello. Actually, I had the same question, so.
So much for that.
So thank you for answering.
Okay. Any other questions here? Thank you very much.